Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. You remember that when we covered the dot product, we learned a procedure that would let us take any vector in space and break it down into two components, one along a given direction and one orthogonal to that direction. And we said because in many problems of science, engineering, we have vectors that are not necessarily along the x and y, but they may be on some inclined surfaces, and these surfaces are perpendicular to each other. So we would like to have a way, if we are given vectors even not necessarily perpendicular to each other, two directions. I have all my forces in two directions. I want to transform them into two vectors perpendicular to each other or orthogonal to each other. So when I have a basis like x and y, I and j, or I, j, k, it makes life easy for me because they are perpendicular to each other, and we know that that gives us a way to simplify our work. But suppose I was given three vectors or four vectors in R4, it doesn't matter. Just in Rn, I'm given some vectors, but these are not perpendicular to each other, and I want to make them orthogonal, meaning make them perpendicular to each other. And then take it a step further and make each one of them a unit vector. So I have 3-unit vectors or 4-unit vectors or 5-unit vectors in hyperspace, but they are orthogonal to each other. Okay? So we call this process orthonormalization of vectors or bases. Now, orthogonal meaning perpendicular. They are mutually perpendicular. So each direction is perpendicular to each other. But if I make them perpendicular and unit vectors, they are called orthonormal. Instead of orthogonal, they are orthonormal because I normalize them. You normalize them by dividing a vector by its norm. Remember the norm, meaning the magnitude of the vector? So when you divide by the norm, you are normalizing that. And we use this term in many things in probability and in other areas, when we normalize things. Okay, so just a quick thing. Suppose, remember when we had in dot product, we had, for example, a vector not in xy, it's in 2D, but 2D or 3D, it doesn't matter, but 2D would be easier to just remind you of what we did. So suppose this direction, let's call it W. And I have a vector in space or in 2D. Again, it doesn't matter what you call it, which dimension. I have a vector V here. And I say, I want to decompose B into two components, one along W and one perpendicular to W. And I told you that when we went through this session, I told you to find the projection of V onto W. You draw a line from the end of V perpendicular to W. And this part would be called the projection. That's the projection of V onto W. And I told you, think about it as this is a wall, and you have some object here, V, that has this length. So you bring a source of light and you make it, or you place it at the end of your object, V, in such a way that it becomes perpendicular to W. So it's perpendicular to W, and you measure the length of the shadow of this object. It would be the projection. You are projecting it on this wall. So that's what you see. You don't see anything else when you look at V. You see this shadow. And this is called the projection of V onto W. And this part is the orthogonal one to it. So these two are perpendicular to each other. So how do I find this piece? Remember, many people say use Pythagoras, and some others say, oh, you multiply by the sine instead of cosine because in the dot product we use. Nah, it's much easier than that. I know that the sum of these two vectors give me V, so this part is V minus the projection of V onto W, right? That's it. Now, if I divide each one of those by its length, it will give me the direction. One of them is the direction of W, and one of them is a direction perpendicular to W, and I solved my problem. The question is, if we are in Rn, not R2, I may have direction given to me, 3 directions or 4 directions, and I want to make them orthonormal. I want them to be perpendicular to each other and at the same time of unit length. Let me first write this to remind you. This was V dot W over W square, which can be written as W dot W times W as a vector. So the dot product of these two guys divided by the length of W times W. If I make W a unit vector, so if I call this is EW, a unit vector along W, then this can be written as V dot EW over EW dot EW. Since it's a unit vector, it would be 1, right? So I can simplify it by saying this guy is V minus V dot a unit vector of W times a unit vector of W. Anyway, this procedure or this process of making any number of vectors orthogonal to each other and then orthonormal, meaning of unit length, is called the Gram-Schmidt Orthonormalization Process. We're going to take a couple of examples here to see how we do that. So suppose we are in R3, or we have 3 vectors in R3, V1, V2, and V3. I will say that W1, my new vector, I'm going to call it W1 equals V1. That's it. And from here, I can find U1, meaning a unit vector, as W1 over its magnitude. And then when I calculate W2, I say, well, it's V2, but I want to make V2 perpendicular to V1, so minus V2 dot W1, because W1 is V1. In this case, it doesn't matter, over W1 dot W1 times W1. And then when I go to W3, I say it's V3 minus V3 dot W1 over W1 dot W1 times W1. But guess what? Now, these two are perpendicular to W1, but they are not perpendicular to each other. So when I get to the third one, I also have to subtract V3 dot W3 over W3 I'm sorry, over W dot W2, where W2 dot W2 times W2, and now these three would be perpendicular to each other. If I take W2 and divide it by its magnitude, I get U2. And if I take W3 and divide it by its magnitude, I get U3. And some people would say, why do I have to do it all this way? Once I find U1, can't I substitute for W1? So I say V2 dot U1 over U1 dot U1, which is a 1, times U1. And then I replace all the W's with U's. Yes, you can. It may simplify it a little bit. I want to take it, the long way so that you can see what's going on, but maybe if we have time, we will show how to simplify the problem. So here I was given three independent vectors forming a basis in R3. I'm not going to change it into another basis like we did before. No, these three bases are not perpendicular to each other. How do I know? These two are, because the dot product gives me 0, but these two aren't. They will give me 3, and these two aren't. They will give me 1, so they are not perpendicular to each other. So I will start by saying W1 equals 0, 3, 4. Pythagoras say 3 square plus 4 square is 5 square, so I can write U1 right away as 0, 3/5, 4/5. For some people prefer to take the 5 out and say 1/5 so that they leave the 0, 3, 4 as it is. It doesn't matter. Now when I move to W2, I'm going to say W2 equals 1, 0, 0. And then I'm going to use the W, not the U, just to make it the long way, so to speak. And I'm not going to write the equation, you already know it. So because I called this guy V1, this guy V2, and this guy V3. So V2 dot V1, right? Or dot W1, since W1 is the same. So I can do 0 plus 0 plus 0. So minus 0 over 5, which is 0 times 0, 3, 4. So it stays the same. So U2 is the same as W2 because it's 1, 0, 0. So it has a magnitude of 1. So that was easy. And we knew from the get-go that the dot product was 0. So it's already perpendicular. So I don't have to worry. Finally, I do the W3 and I say W3 equals V3, 1, 1, 0 minus the dot product of these two guys, 0 plus 3 plus 0 is 3, over the magnitude of V1 square. In fact, here we wrote V1, it should be, we wrote 5, it should be 25. So over 25 times 0, 3, 4 minus the dot product of these two, 0. Oh, I'm sorry. 1 plus 0 plus 0 is 1. Why did I minus? And this is this. Over the magnitude of that, which is also 1, times 1, 0, 0. So that's an easy one. Let's work it out. 1 minus 0 minus 1 is 0. 1 minus 9 over 25 is 16 over 25. And 0 minus 12 over 25 is negative 12 over 25. So U3 equals. Well, what is the magnitude of that? The magnitude of that is 4/5. How do I know? Well, do you see that I have 12 and 16? So I can say 16 square over 25 to over 25 square plus 144 over 625. When you add them up, you get 400 over 625. And then when you take the square root, you get 20 over 25, which is 4/5. So it's 4 over 5 times 0, 16, negative 12. So, oh, I'm sorry. I already took, I meant 1/5 over that. Or I can take 4 out and write it as 4/5 over 0, 4, negative 3. So that's U3. Now, if we perform a dot product, of course, we know these two give me 0. These two would give me 0 because there's only entry in the first, and here there is a 0 in both. But how about these two? Forget about the constants. 0 times 0 is 0. 3 times 4 is 12. 4 times negative 3 is negative 12, so they add up to 0. So now my new bases, again, you can take the 5 out or leave it inside. So the bases here, or the orthonormal bases, would be 0, 3/5, 4/5, comma, 1, 0, 0, comma, 0, 4/5, negative 3/5. And that's how we apply it. The second example I wanted to go over is how to find an orthonormal basis for the solution space of that. Remember the solution space when we found the null space of a matrix? Here we have two equations in 4 unknowns. So we have to go through Gauss-Jordan elimination method. So I'm going to say that my matrix A is 1, 1, 0, 7, 2, 1, 2, 6. So the first step, we are going to make that a 0 by subtracting 2R1. And that takes us to the first row stays the same. The second row is 2 minus 2 is 0, 1 minus 2 is negative 1, 2 minus 0 is 2, and 6 minus 12 is negative 5. And finally, I'm going to add, oh, wait a second. We said, what did I do? 2 minus 0, multiply this by 2, and 6 minus 14 is negative 8. I say negative 12. I multiply the 6 by 2, not the 7. Sorry. Then I'm going to add R2 to get rid of this. First of all, I think it's better to multiply that at the same time by negative 1, right? So we have a 1 here as a pivot. So this would be 0, 1, negative 2, 8. And then when I add these two, I get 1, 0, 2, and negative 1. And now I see that I have two pivots, meaning the solution space can be written as, or the null of A here can be written as, we call that S, and this is T. So like we did before, x1 is negative 2s, and x2 is positive 2s, s is 1, t is 0, comma t, x1 is t, x2 is negative 8t, s is no t, and t is 1. So now here is my basis. Negative 2, 2, 1, 0, and 1, negative 8, 0, 1. Of course, these two are not perpendicular to each other. So in order to make them perpendicular, we are going to say, okay, W1 equals -2, 2, 1, 0. So U1, to know, because they want an orthonormal basis. So U1, the magnitude of that is 4 plus 4 plus 1 is 9. Under the radical is 3. So it's -2/3, 2/3, 1/3, and 0, which also can be written, as we mentioned, as I can take the, if you don't want fractions inside, then you'll get -2, 2, 1, 0 over 3. Now, when I go to W2, it's going to be V2, the second basis, 1, -8, 0, 1, minus the dot product, which is -2 minus 16 is -18. Notice that negative times negative is positive, so we can do that right away. And the dot product of this thing by itself is 9. We know that the magnitude is 3, so that's the square of that, times -2, 2, 1, 0 equals, so this is 2, 1 minus 4 is -3, -8 plus 4 is -4, 0 plus 2 is 2, and 1 plus 0 is 1. Now, if you square, I know 3 and 4 will give me 25, like 5 square, plus 4 is 29, plus 1 is 30. I take it out as 1 over the square root of 30 times -3, -4, 2, 1. Or if I want to write it in this form, it would be -3 over root 30, -4 over root 30, 2 over root 30, and 1 over root 30. Now, the final step is to check to see if these two vectors are perpendicular to each other, if their dot product gives me 0. So I get -2 times -3 is +6, 2 times, I'm sorry, yeah, 2 times -4 is -8, 1 times 2 is 2, and 0 times 1 is 0, 6 plus 2 is 8, minus 8 is 0. So I know that these two vectors are orthonormal vectors of the solution space of that four unknowns, two equations in four unknown linear equations. I hope it wasn't that dry as usual. I say that. I hope you got it. It's really very easy once you understand. If you already understand the dot product and what we did in projecting a vector into two directions, you can expand that to any number of vectors. It may be tedious a little bit, but the process itself should be easy. So we have to thank Gram-Schmidt for applying that and give us this thing. And we still have quite a bit to cover in this course. I wish you all the best. Thanks for watching. If you have any questions, feel free to send me a comment and I will try to get back to you as soon as I can. Have a great day.